I'm going to talk about a theory for some very recent experiments which see non-reciprocal critical currents in a whole class of superconductors without applying an external magnetic field. And I will discuss the symmetry, topology, and a little bit the microscopics for this, what is called the zero field diode effect. And it's been observed in multilayer graphene, in rhombohedral graphene, in a Kagome compound, and in underdoped cuprates. My interest in this subject came about because of a visit to Beijing and introduction to these experiments by Jian Wang and the students, both in the Kagome compound and the underdoped cuprate, and also my interactions with Long Ju at MIT on rhombohedral graphene. The principal message of this talk is going to be that this effect does not occur unless they are topological superconductors, which follows if above TC they are metals with time reversal and inversion broken, which in effect means that these materials should have properties with the symmetry of the anomalous Hall effect already in the normal state. This is going to be a very simple talk, and it is organized as follows. I'm going to very quickly and briefly show you two examples of the zero field non-reciprocal critical current, one on rhombohedral graphene done by Long Ju at MIT, and one on cuprates, which is the data from Dr. Jian Wang and his students. I will briefly mention the very well understood finite field non-reciprocal critical current, because if we know about this, we can say that the symmetries which are produced by applying a magnetic field to observe, and other things, to observe non-reciprocal critical currents should spontaneously happen in the case of the zero field non-reciprocal critical currents. And that's what I'll talk about here. And then I will talk about the microscopics for the topology in cuprates. In the paper that I've written on it, the hexagonal Brillouin zone is also treated, but I will emphasize the microscopics for the topology in cuprates in the pseudogap and superconducting state. And I'm going to do this primarily because in rhombohedral graphene and in Kagome, as well as in cuprates, the essential element are loop currents and for the time reversal breaking. And while this is rather easily accepted by almost everybody for the Kagome compound and for the rhombohedral graphene, it has become, because of the historical development on the theory of the cuprates, there is some resistance for people who have been working for 35 years on cuprates, and I hope to be able to reduce some of that. So let me first talk about a clearest example of the zero field non-reciprocal critical current. So you take this superconductor and you pass a current in this direction, and you observe when you begin to develop a finite voltage. And then you pass the current in the opposite direction, and you observe when the sample begins to develop a finite resistance. In principle, a very simple experiment. In practice, I'm told it's not easy to get the conditions exactly right. But you see here, this gentleman has plotted for you derivative of the voltage with respect to current versus current at various temperatures below the transition temperature of about 300 millikelvin, and there is the systematically you will observe that the critical current in one direction is quite different from the critical current in the other direction. In this compound, when he goes above Tc, and he has measured it in various different samples, this is the cleanest example of his non-reciprocal critical current. When he goes to the normal state at 480 millikelvin, he can measure Rxy, the Hall resistance, and he discovers that the Hall resistance is unquantized. However, it is spontaneous in the sense that by the time you apply 100 Gauss, the Rxy sign switches from one to the other. So this is the hysteresis characteristic of going from one to the other, and this is rather simple and beautiful. Let me go to, and so this is clearly a case of a topological superconductor with anomalous Hall effect in the normal state.
Does it have to be that sample? Does it have to be trained?
Sorry?
Does it have to be trained? Like you have to...
In the case of Liangzhu's sample, he did not have to train it. However, it tells me that as he repeatedly heats and cools, it appears in arbitrary direction.
Okay, thank you.
But he did not train it. Let me say that in the Kagome, it's actually a very, very important and pertinent question. So let me go to Dr. Wang's measurements on the Kagome compound, which I'm not going to speak about. He heats and cools and in zero field, and he observes arbitrary directions. However, if he applies a magnetic field well above the superconducting transition temperature, cools it a bit, removes the magnetic field, goes into the superconducting state, measures the critical current, it's in a specific direction, and then goes up above, applies the field in the opposite direction, it is in the opposite direction. So it means that something already in the normal state sets the pattern for the direction of the current. Not only is his direction of current similar, following this trend, even the magnitude depends upon the training field, which clearly calls for some effects associated with having and progressively removing domains already in the normal state.
Thank you.
So here is the data in the cuprate, and Dr. Wang does not plot you dVdi derivative, which would look much more impressive. He plots for you the voltage developed as a function of current, and this is current in one direction. Is nicely put for you a modulus here, and then he applies the current in the other direction, and you see that this superconductor with a underdoped Tc of 80 Kelvin, this measurement is taken at 53 Kelvin, and you observe a huge value of the non-reciprocal critical current. You see that it's on the scale of 20 microamps. The previous thing was in a few nanoamps, okay, in the rhombohedral graphene. This having this very large non-reciprocal critical current is, it turns out, both a blessing and a curse, and I can explain why I say so, if there are questions on that. He very nicely then takes the sample and applies a AC current at a low frequency, AC current, positive, negative, and he's somewhere here, so he should observe in one direction 0 resistance, and the other direction the finite resistance, and that's what he observes. And I've seen data on this going on for several hours. Is that about right? Several hours or several days? Well, anyway, it's good enough.
Tomorrow.
All right. Now, in this compound, unlike rhombohedral graphene, a DC anomalous Hall effect is not seen. However, and that's related to the curse that I mentioned, but Kerr effect is observed in 4 different families of cuprates. Now, Kerr effect has the same symmetries required as the anomalous Hall effect. And here is Aaron Kapitalnik's and friends Kerr effect at setting in a specific temperature. And this temperature happens to be the pseudo-gap temperature for that doping. And he has done this for various samples, various different dopings in a given sample. This happens to be YBCO. He also has data for BISCO. And you see that Kerr effect is found in this range. I should say that there are a variety of experiments that have the neutron scattering and a wonderful experiment by Shivauchi on changing lattice symmetry on applying magnetic field below the superconducting transition temperature, below the pseudo-gap temperature, and a few other time reversal specific experiments.
Chandra? About the Kerr effect, if I remember correctly, at that time, I think it was reported that the Kerr signal itself was not trainable by magnetic field, right?
That's a very important point, and ask me again at the end, and I will explain to you what precisely that meant. I've had to think about that a lot, and I have some things to say about it. So that's all I'm going to say about the new experiments. But let me briefly mention the H not equal to 0 reciprocal critical currents, which are routinely observed in. Now, why is this not changing away? I'm unable to shift this.
Maybe jump out of the, maybe jump out and jump back in. Well,
Okay,
try to go back
that's
in.
the way to do that. Okay, now I have accomplished for the moment what I want to do.
I mean, see if it works now, if you can go back and forth.
Yeah, okay, thanks. Okay, so in almost any superconductor, you can apply a magnetic field and measure the non-reciprocal critical current. Here is an example on something or the other. This is from the MIT group. I've forgotten. This may be metallic niobium for all I know. Superconducting niobium. And you observe.
Should be niobium. Yeah.
You observe this IC plus and IC minus differing. Here, current is plotted here and voltage is plotted reversed from the previous one. And you also observe that in these experiments, the difference of the critical current is linear in the applied magnetic field, meaning it changes sign as you change the direction of the field. Whereas in Dr. Wang's experiments in the cuprate, it decreases quadratically with field in both direction if you apply a tiny field. About 0 field, you observe it, and then it decreases quadratically. So in this, what is required for the H not equal to 0 effect is that there be a Meissner current plus some source of breaking reflection. Okay? When that happens, when you apply current in this direction, the Meissner current adds and subtracts. Whichever current added exceeds the critical current, the whole material goes normal, even if the other one is less than that. Okay? It's simple to understand. And now if you apply the field in the other direction, and there is some inversion breaking, effectively the magnitude of the Meissner current is different, or less current is going in quite often because your contacts are different on the left and right. In any case, what you require is both Meissner effect plus breaking reflection. At this point, you should note that Meissner currents have the topology of anomalous Hall currents. Okay? What that does mean? It is a chiral current which is antisymmetric. Okay? Sigma xy is minus sigma yx. Okay? And then you require reflection rate. Okay, so I think we already know now the physics of what we require to happen at zero field. We should have topology of currents with Hall effect, symmetry without applying magnetic fields. We should have broken inversion, and these two remarks can be put in the form of a simple equation, which is that besides the usual superfluid response to a vector potential, and if I, for ease of writing, take this vector potential to be in the transverse gauge, then there's a current at zero frequency which follows the principal axis of the crystal. So there's a superfluid density which depends on the direction of the principal axis, and it's diagonal. You also require an anti-symmetric chiral superfluid response. So this epsilon ij. So there's an extra, you need your superfluid tensor to become chiral and anti-symmetric, and also it must be polar. It must break some reflection symmetries. Okay? So these are also the conditions for the anomalous Hall effect in the normal state. And the superconductor, if these happen in the normal state, superconductor must inherit these symmetries to lead to the spontaneous diode effect. So let me illustrate these two things about how they happen experimentally. When you have this kind of normal object, and you apply current through normal leads, current is going in, but current will go in over some penetration depth, and it will travel like that. That is the normal way that you get dissipation, less current in a superconductor. It's really a manifestation of the Meissner effect. But now we need the superfluid density to also produce you a chiral, meaning that you apply current like that, some of the current goes like this, and on the other direction it will go like this. And of course current has to be continuous, so it will flow like this if there is infinite resistance on the other sides. Okay? So this plus inversion breaking is good enough to get you the diode effect.
Okay, but how do you get current continuity there? I'm a little confused. Oh, this is on top of the overall.
Okay, so now I'm going to briefly discuss, for reasons that I already mentioned, the microscopics for cuprates. So this is really the phase diagram of cuprates, the antiferromagnet, the superconducting region, and within a year or two of peculiar properties being discovered here, there were two paradigms proposed, one by Anderson of RVB. These were really sort of setting up the stage for what should be understood and investigated. And another was that this region has properties which are completely unlike Fermi liquid, but very simple, very simply stated algebraically. The most famous of them is resistivity, but almost anything you study, nuclear relaxation rate, Raman scattering, optical conductivity, they're all peculiar. And with a bunch of colleagues, I suggested that that can only happen if there is a singularity at zero temperature in certain response functions. So that posited a quantum critical point, and with that hypothesis that the fluctuation spectra, the imaginary part of the fluctuation spectra goes as omega over t, or the real part of some fluctuation spectra goes logarithmically with temperature, a quantum critical point was proposed. That required one to understand that there be a transition of some kind across this line, which had to have some rather remarkable symmetries, and I proposed that there can be loop current orders in this regime, and this particular symmetry was proposed. Now, this particular symmetry breaks time reversal and inversion. This is not sufficient to get you the anomalous Hall effect or the diode effect. Okay? It is also not sufficient to get small Fermi arcs or small Fermi surfaces, which are of properties here, but it is sufficient to calculate and to understand the occurrence of edge currents in an infinite bar. And so let me go to that directly right now. And this was already sort of suggested in a paper by Brigitte Laridon, Tai Young, and me quite some time ago. You see, if the superconductor breaks time reversal and inversion, and the principal order parameter is deep parameter, and for my ease, I have oriented A and B axis so that it's dxy, then there must be a px or py component added to it with an amplitude which depends on the magnitude of the broken order parameter. And you can quite clearly see that if there is a d-wave order parameter and p-wave order parameter, an invariant exists, a Chern-Simon term, which is composed of a effective superfluid density psi d times psi p times I times a current flowing in the y direction, because you see this I takes care of the time reversal of J, and this J is also polar in the y direction, and so is dxy times px. Okay? So there must be a Jy. At this point, you can immediately see that this does not happen for the S plus IS or P plus IP superconductor. Now, but the question arises, what is Jy, where does it flow, and what is its magnitude? And for that, one can, again for this order parameter, assume an infinite bar and solve the Bogoliubov-Dijen equations. X is a conserved quantity, so kx is a good quantum number, and for ky, I can put I d over dy because I have to examine how it decays in that direction, and I solve the Bogoliubov-Dijen equation, and now this turns out that this model has a gap ky equal to, at ky equals 0 at any kx. And when you solve the Bogoliubov-Dijen equations, you immediately come to a edge mode which has a linear dispersion, but equally, or perhaps even more interestingly, the wave function, u is the coefficient, let us say, of c of k and v of c of minus k dagger. That coefficient, and I missed here when this is minus plus, this should also be minus plus here. And you look at this and you see that at kx equal to 0, u over v is 1. That means at k equal to 0, it's a Majorana. Supposing you go to the limit, this kx is measured in units of inverse lattice constant. If this coefficient is very large, then u over v is I, or plus or minus I. That is a chiral fermion. You see, because if you have c of k plus c of minus k dagger, it's a Majorana. If you have a c of k minus or plus I c of minus k dagger, it is a fermion flowing in one direction, depending on the sign of I, either this way or this way, okay? So you will, in general, get edge currents which are unquantized, okay? But they are of topological origin. And this can be verified, okay, so let me quickly go back and say that, as I said, this is not a sufficient thing to get me the anomalous Hall effect and various other properties of underdoped cuprate. In particular for current, if this was minus ky, then the current would be flowing in the opposite direction. If it was kx, then current would be flowing in the y direction or minus y direction, okay? And many years ago, again, I proposed, in order to understand some other properties of cuprates, that this pattern should be organized on a long period, 2 times p, the period, and arranged in this direction. And it turns out that because of current conservation required around the domains, you cannot have domains of this thing without currents at the boundaries, okay? Because of current conservation, this is topological. You can distort it in all possible, any fashion you like, as long as you can maintain this topology. And it turns out that it gives me chiral time reversal breaking, breaks T inversion, and breaks time reversal time inversion, and it gives me small Fermi surfaces, and it explains a few things that have not been understood before. Let me skip this, since Chairman has been flashing 5 at me. I'll come back to that if there are questions about how this gives you these things. So with this thing, I can now calculate by Kubo formula with this kind of order parameter what the current would be, the surface current, and you can calculate both what I call a Berry current or the electromagnetic current, and the Berry current is quantized, but the electromagnetic current is not quantized. It is this way. It depends on the ratio of delta P over delta D, or it is, changes sign, of course. And the physics of the difference between the quantized Berry current, which I'm not interested in, and the quantized electromagnetic current, which my voltmeter and ammeter can measure. They don't know anything about Berry currents. They know about real currents. You'd measure some unquantized, and this follows from my Bogolubov-Dijen boundary equation that I already explained to you. Now, I can summarize whatever I have said by saying that the conditions for the spontaneous diode effect are the same as for anomalous Hall effect in normal state, local time reversion invariance, and inversion breaking. And I've introduced for you the concept of an antisymmetric chiral superfluid tensor. I've presented a microscopic calculation on cuprates with extended or long period loop current order showing integer Chern numbers but fractional edge current, giving a diode effect. Being a macroscopic observable, all you're doing is you're taking a sample and passing current this way and observing that critical currents are different. It's a macroscopic experiment. This reinforces the conclusion about time reversal symmetry breaking at the central physics of cuprates, also Kagome and many other compounds. Let me also say that if you're looking for a topological superconductor, the easiest way to experimentally detect it is the diode effect. You don't have to look for Majoranas and beat your head against all kinds of problems. Just look for diode current. Okay. There are some important experiments yet to be done for the diode effect to be sure that we have a complete understanding of cuprates, and I can enumerate them if you like. Thank you very much, and I hope I have left enough time for extended time for discussion.
Sure. Yeah.